Hello everyone. Today we'll be studying the bending stresses in the beams. Okay, this will be our the fourth unit. It is bending stresses in the beams. Okay, the important thing in the beam is the beam is a little bit different than the your other components like columns because the column is different and the beam is different. So the loading and the stress induced on these beams is different. So, what is that difference, or what type of stresses are induced only in the beams? We'll try to understand today. Okay, and you see the title of this unit, that is bending stresses in the beams. That itself tells that whenever there is a uh, stresses are induced, okay, and load is applied, there is a bending of the beam happening. Okay, the bend will beam and there will be a deformation. So due to that bending, there will be a stresses develop, and due to the bending, the stresses are developed. That stresses is called as bending stress. Okay, simple. But if you go as technically, if the beam when applied load, there is no shear force. Okay, there is no shear force. Okay, and there is a constant bending moment. Then it is called as a pure bending. Remember this. You understood first what is bending stress. Whenever beam is loaded, okay, or load is applied over which over a beam, and due to that stresses are induced, and due to this stresses the bending happens occurs. Okay, due to that bending stresses occurs, this is called bending stress. When there is bending, and to resist that there are stresses induced, so that stresses are called as bending stresses. Now what is pure bending? When a beam is been loaded or applied load, and there is due to that loading there is no shear force. Okay, shear is not being occurring at any point of any instance, and the bending moment due to the loading is constant. Then that type of beam is called, or that type of loading is called, or bending is called as pure bending. There is no shear. Shear will be zero. So that type of bending will be called as pure bending. Okay, if the beam is subjected to the constant bending moment and no shear force, then the stresses will be set up at that length of the beam is due to the bending moment only. Then the beam is said to be in pure bending. Okay, and the stresses developed due to this bending is called as bending stresses. Understood? So in this simple bending, to beam to be a simple bending, there are some of the assumptions made. The simple bending theory. To have a simple bending beam, there are some of the assumptions made, because we in the real will not get the pure bending beams, because there will be a shear force in the beams. Whenever you load, there will be a shear force. There is no instance that there will be a no shear force will be zero, and there will be only a bending moment that also will be constant, not be necessary, right? It is not real, it is imaginary, right? So there are some of the assumptions made in the simple bending theory. So what is the first assumption? That the the material of the beam is homogeneous and isotropic. In the all the directions, the properties of the material will remain same. Okay, that is what homogeneous and isotropic means. The properties of the material of the beam will remain same throughout, right? And the value of Young's modulus will remain same in tension and compression, but it will not remain same. Okay, transverse section or the cross section of the beam will remain plane before bending and remain plane after bending. If you see, a beam is like this previously, and when you bend it, its cross section was like this, now it has become like this, right? So this is a difference actually happens when you bend the beam. But what we are considering here, what we are considering, that it will not bend along its transverse or cross sectional plane. Next is beam is initially straight along the longitudinal filament or the fiber, along the longitudinal fiber bend in a circular arch. Okay, what it is saying is the beam previously was a straight line. It was in along the straight longitudinal length axis, and the uh, ends of the beam or the side ends of the beams will be in arc or curvature. This, right, in like this when it is loaded, and it will be have a, because it is in curve, it will have some curvature and which will have some radius. This will be your R, and this C curve will be called as curvature. Okay, so the radius of curvature is larger with compared to the cross sectional. Okay, this is what assumption is done. Next is the each layer of the beam is free to expand and contract independent of the layers above or below to it. It says that the if you divide the beam into different layers, or if you see that beams are in different layers, okay, the beam is free to bend or not to bend. Okay, it is not dependent on the previous or the above fibers of the beam. It is independent of itself. If it wants to bend, it will bend, or if it doesn't want to bend, it will not bend. This is what are the assumptions made in the simple bending theory. Next, we'll try to understand what is bending theory. Okay, what is simple bending theory? If you see here, there is a beam, right? There are to this beam we have taken a section AB and CD at two different points at a distance delta x. Okay, and we are applying a like movements, unlike movements at the ends. We are applying the movements m at the both the ends in a clockwise and anti-clockwise direction. Okay, so before loading the beam is, you see, before loading, this is a beam and this is what your movement applied, right? And this is your section AB and this is B and CD. Once you apply these movements 1 and 2 m, right, once you apply the movements, the beam will bend like this, like a curve, right, as we have assumed it. Actually, when we apply the movements of the loads, it will not uh, bend at this extent. The bending will be there, or the curvature will form, but it is very negligible. But for our uh, purpose, study purpose, we are going to consider it like that. So it will bend due to the movement, right? This is your movement applied. This will be your section AB, section CD, right? And at the center where your center of gravity will pass. Okay, and that surface is called as neutral axis surface, centroidal axis, or the CG, where it pass, that layer or that surface will be called as neutral surface. Okay, that layer will be called as neutral surface. If you can see A, B, and CD, if you can see AC, the distance previously bending was larger. Now the distance between A and C has reduced. When will be there will be reduction in the length? When there are compressive stresses applied, right? When you compress any object, the there is deformation and there is a reduction in the size, right? If there is a tension, there is an increase in the length. There is compression, there is a decrease in the length. So as there is a decrease in point A and C, at the upper layer, it is the upper fiber of the beam will be along the compressive stress. Okay, now along the section BD, at this at the extreme fiber, bottom fiber, that is the section BD, the length has between the section BD has increased. Means what? Temperature stresses are seen, or tensile stresses are seen at the bottom of the beam. That means there is a compressive stress at the top, there is a tension stress in the tensile stress in the bottom. This is how the uh, stresses distribution is there along the cross section of the beam. Okay, this is how the stresses are being distributed along the cross section. Okay, here will be the maximum compressive stresses, and here there will be a maximum tensile stresses at the bottom when you bend it in the curved shape. As you go at the center, you can see it is going on reducing. When you come from the top to the center, it is 0. When you come from the bottom to the top, it is 0. That means there are no stresses induced. At the neutral axis, this will come at the center, right? This will be at the center. So at this centroid or at the CG, the stresses will be 0. There are no stresses induced at the center of the beam. Okay, this is what bending theory says. Okay, that whenever you bend a beam, the topmost fiber of the beam will be under compressive loads, and the bottommost fiber of the beam will be under tensile loads, and the central axis, as you can see the stress distribution diagram, sorry, as you can see a stress distribution diagram, as you go at the center, the stresses are reducing, and it is at the end point it has become 0. It will be exactly at the center. So as I said, the neutral surface, okay, and the axis along which it is passing, that axis is called as neutral axis. Okay, this is what is bending theory is. 3 points to be remembered: top compressive stresses, bottom tensile stresses at the fiber, bottom fiber and the top fiber, and at the center no stresses, 0 stresses will be induced. This is what the simple stresses says. Okay, and next is moment of resistance, the total moment which can be carried by an section of a given beam for a maximum value of stresses. When you apply a maximum stresses, okay, when you apply a stress, the beam which can resist that up to maximum extent, that is called the moment of resistance. How much resistance the beam can apply or provide to the given loading. Okay, that is called as moment of resistance. Okay, depending upon the above theory, we have derived the simple equation, that is simple bending equation, that is m upon I f upon y is equal to E upon r. What is m? M is nothing but bending moment, or it can be equal to moment of inertia. When we equate, the bending moment is equal to moment of inertia, because what is bending moment? The maximum bending moment is only itself is a moment of resistance, because the maximum bending moment which can beam bear, that is called as maximum resistance, right? It is a maximum resistance that beam can apply. So it will be equal in some of the cases when we are solving the problems. So it is bending moment upon I is equal to bending stresses upon the distance of the layer from the neutral axis of the beam sections. Okay, from the neutral axis to the whichever extreme fiber, that distance is called as y. And what is F? It is the bending stresses. And what is E? E is the Young's modulus for the beam, and R is the radius of curvature of the beam. Okay, this is a simple bending equation. This M upon I is equal to F upon Y is equal to E upon R. Using this formula, we'll be calculating the various required terms that is required for the calculate the bending stresses. Okay, now this is what is sectional modulus to be remembered. One more term, that is sectional modulus. What is sectional modulus? The ratio of moment of inertia by the uh, distance between the neutral axis to the extreme fiber. Okay, it is a distance between the neutral axis to the extreme fiber of that member is called sectional modulus. If I upon y, you can say it is nothing but it is ratio of moment of inertia by the distance between the neutral axis to the extreme fiber, that is called y. So it is the ratio of I upon y. So these are the different I upon y ratio uh, that is equal to denoted by z, that is called section modulus. Why is this important? Why is the section modulus required? I upon y is necessary. By this we will try to the section modulus will tell us whether the beam is strong enough for the bending stresses to bear enough, right? This will tell us which beam is has a good resistance to the bending stresses. Okay, so to find out the section modulus is required. Okay, it is nothing but ratio of I upon y. Okay, these are the various formulas for the section modulus of the for the given sections. Okay, will we try to solve the problems here. A beam of rectangular section of 100 mm wide and 200 mm depth is used to carry a UDL load of 8 kN per meter, including its self own weight. Find the longest span to which it is used to, okay, if the permissible bending stresses does not exceed 10 Newton per mm square. Okay, so what it is here saying is the different length and breadth is given, that is your cross sectional values are given, the load is given, okay, and they are given what, they are given bending stresses. So you have to first calculate the section modulus. The first thing is you have to find out the section modulus in the any problem. Okay, and they have said that Find out the longest span. When you will calculate the longest span, when you will be calculating for the maximum loading. Okay, so once first we will try to solve the part one by one. First we have to find out the section modulus. It is said it is rectangular section, right? A timber beam of rectangular section. So what is the formula for the section modulus for a rectangular section, solid rectangular section? It is BD square by 6 is the formula. BD square by 6 is the formula for section modulus. Substitute the values and get the section modulus in mm power cube, right? Then calculate the moment of resistance. Why moment of resistance? It is a maximum resistance given by the beam to the given stresses. Okay, to calculate the moment of uh, resistance, you have to use the simple bending theory equation. It is m upon I is equal to F upon Y. Okay, so to calculate m is equal to Z into F. Why? Because it is like this. Okay, it is m upon I is equal to F upon Y. So you know that Z is nothing but ratio of I upon Y, right? So what we'll do, we'll just in cross multiply and we'll get the equation as m is equal to F I upon Y into F. It is, what is this? This is Z. So m is equal to Z into F. That is how we get the moment of resistance formula. M is equal to Z into F. By this we calculate the moment of resistance. Right. What he has said, it is to calculate for the maximum, because we have to calculate the maximum length. To calculate maximum length, we have to have a moment. So what we'll do, we have not don't have moment, so we'll be equating the moment of resistance, because you have to calculate for the maximum load or maximum span, whichever it may be. You have to equate the moment of resistance that you have calculated from the m is equal to Z by F equation, and use that formula as a moment, because that will be the maximum moment, the maximum stresses that you can bear. So using that uh, value, you are going to calculate the length of the beam, right? So what is a moment formula for the simply supported beam? It is WL square by 8, right? So you are going to equate the moment formula by moment of resistance. So what is the moment of resistance given? 6.66 is equal to, what is the load? It is 8 into L square. What is we are going to find? That is your length of the beam, L square by 8. 8 by 8 gets cross. 8 and 8 gets cross. It becomes L square is equal to 6.66. So if you square root it, you will get what? 2.58 meters is the span of the beam for the maximum moment of resistance you can provide. If the length of the beam increases for that moment of moment, it is what is your moment of resistance, then your call beam will fail by bending stresses. That is what said in the says in the uh, problem. Okay, this type of questions will be asked. You will be asked to calculate W, or you will be asked to calculate the L, right? This is how you are going to solve the different types of problems in this bending stresses in the beams. You have to remember that to be perfect, you have to solve n number of problems. Here we are trying to brush up your concepts, so only one problem for an example. Okay, just go through the problems. If there is any problem, any difficulty you face while solving the problems, you can post it in the comment box, or you can contact me, and if you if you can post in the comment box, we'll try to help you out. Okay, thank you.